The human brain stands out as one of the most intelligent organs on Earth. However, there are certain concepts that elude our understanding. Among them is the paradox, a perplexing puzzle that challenges our evolved perception of reality. While we've adapted to comprehend the world in a specific way, certain paradoxes suggest that reality might defy our conventional understanding. Presently, a group of physicists claims to have unraveled a paradox that has intrigued scientists for half a century. Yet, questions linger. Have they truly cracked the code, or does the mystery persist? Moreover, what are the other peculiar paradoxes that baffle our comprehension? Enter the Fermi paradox. Many of you may already be acquainted with the Fermi paradox, named after the renowned Italian physicist Enrico Fermi, celebrated for pioneering the first nuclear reactor. This paradox grapples with a fundamental question: where are the aliens? Considering that our star and Earth are relatively young in the grand scheme of the universe, and acknowledging the potential for a civilization to achieve interstellar travel, it seems logical to expect a visit from extraterrestrial intelligence. However, despite these factors, we find ourselves still awaiting contact. Critics argue that it might not be a true paradox, as our assumptions about the existence of intelligent life remain speculative. The Drake equation plays a pivotal role in tackling this paradox by offering an estimate of the potential civilizations in our galaxy. Utilizing 7 variables, this equation calculates the likely number of civilizations that could be detectable in the Milky Way. Back in 1961, the Drake equation hinted at the possibility of numerous Earth-like worlds harboring civilizations. However, at that time, no one had knowledge of planets orbiting stars beyond our own solar system. It's only recently, in 2020, that astronomers, leveraging data from the Kepler Space Telescope, made a groundbreaking discovery. They identified over 300 million worlds in the Milky Way with conditions akin to Earth, scattered throughout the galaxy. This analysis revealed that approximately half of the Sun-like stars in the galaxy host rocky planets with inhabitable zones, where liquid water might exist on the surface. Notably, planets are abundantly common and surpass the number of stars in our galaxy. Excitingly, the James Webb Space Telescope is set to embark on a space journey now, aiming to explore and identify new potentially habitable worlds. Stay tuned for an upcoming video on this topic. Make sure to keep an eye out here. Exploring the vastness of the universe, with its multitude of worlds and potential civilizations, a lingering question arises: why is the universe so quiet? As technology progresses, we may be on the verge of unraveling this mystery. Alternatively, could it be that we've already had visits from distant civilizations, and we remain unaware? Recent unexplained UFO sightings fuel speculation that extraterrestrials might already be among us. Definitive proof of such encounters could bring an end to this enigma. Now, let's delve into the bootstrap paradox, a time travel conundrum that questions how something taken from the future and placed in the past could come into existence. This paradox frequently inspires plotlines in science fiction, seen in films like Bill and Ted, Terminator, and Doctor Who. Consider this example. As a time traveler, you purchase a copy of Hamlet by Shakespeare and transport it to the Elizabethan era, where you give it to Shakespeare. He then claims it as his own, and the book eventually ends up back in the same bookstore where you bought it. The question arises: who truly wrote Hamlet? Switching gears to the grandfather paradox, another famous time travel dilemma involves going back in time to erase your grandfather's existence. While everyone loves their grandparents, this scenario serves as an example. As you travel back to eliminate your grandfather, you inadvertently erase your own existence by preventing your father's birth. Imagine a scenario where everything about you, from family and friends to possessions and history, has been completely erased. In this situation, the very existence of your birth becomes impossible, leading to a curious conundrum. Some scientists propose that if such an event were to occur, it might result in the creation of an alternate timeline or even a journey into a parallel universe. Now, consider the taking out Hitler paradox, or a variant of the grandfather paradox involving time travel to eliminate Hitler and prevent World War II. If armed with a time machine and a plan to rectify history, a paradox emerges. The act of removing the need to time travel erases both the motive and the knowledge that such a motive ever existed. Playing the role of a time-traveling executioner creates a complex situation, suggesting that altering the past might spawn a new timeline without Hitler, while the old timeline coexists. But what if you sent something back through a wormhole? Enter Polchinski's paradox, conceived by the late theoretical physicist Joseph Polchinski, renowned for his work on string theory. In this paradoxical scenario, a billiard ball is propelled through a wormhole in such a way that, if it follows its trajectory, it exits the wormhole in the past and collides with its earlier self. This collision alters its course, preventing it from entering the wormhole in the first place, creating a perplexing loop of cause and effect. Nevertheless, physics students have devised solutions to circumvent any inconsistencies in the time travel paradox involving a billiard ball. In these proposed solutions, the ball emerges from the future at a different angle than the one causing the paradox. It delivers a glancing blow to its younger self instead of knocking it away completely, altering its trajectory in the correct manner to travel back in time. Now, let's delve into something that will challenge your perception of reality: the observer's paradox. The observer's paradox is a peculiar aspect of quantum theory, and few things are stranger than Schrödinger's famous thought experiment involving a cat that is neither alive nor deceased. This theoretical scenario involves a cat locked in a box with radioactive material, a Geiger counter, a hammer, and a vial of poison. The radioactive material has a 50% chance to decay, and if detected by the Geiger counter, it triggers a sequence leading to the cat's potential demise. Until the box is opened, the cat exists in a state of being both alive and deceased simultaneously. This strange phenomenon arises because merely observing matter can influence its outcome. Consider another mind-boggling paradox: the double-slit experiment. In this famous physics experiment, imagine a wall with two slits and tennis balls thrown at it. Some balls bounce off, while others pass through the slits. If a second wall is placed behind with slits, marked spots on it should align with the slits. However, when light is shown through the slits, acting as both waves and particles, photons, a single photon creates an interference pattern on the back wall, as if it passed through both slits simultaneously. Even stranger, observing the experiment changes the behavior of the photons, as if they are aware of being watched. Now, ponder the black hole information paradox, a significant puzzle arising from the intersection of quantum mechanics and general relativity. This paradox suggests that physical information could vanish into a black hole, seemingly violating the principle of information conservation according to quantum mechanics, which posits that information can never be destroyed. The resolution to this paradox remains elusive, presenting an intriguing challenge for physicists and perhaps future discoveries. Imagine burning two different letters written on paper. While reconstructing them from ash might seem nearly impossible, it's not entirely so. The subtle distinctions in smoke, temperature, and the amount of ash still carry information about the original letters. Now, let's consider black holes. They have a unique characteristic of pulling things in and, over an incredibly long duration, emitting what they've absorbed in the form of Hawking radiation. Unlike the remnants of burned letters, though, Hawking radiation doesn't contain any information about what the black hole consumed. This uniformity in Hawking radiation suggests that black holes might destroy information about the universe. The question arises: do evaporating black holes genuinely obliterate information, or does information manage to escape as the black hole evaporates? A new generation of physicists argues that information does escape through a black hole via its radiation. They've pinpointed an invisible surface within a black hole, known as the quantum extremal surface, lying inside its event horizon. This surface seems to encode the information that has radiated away from the black hole, evolving precisely as expected if information escapes. Although the dilemma isn't entirely solved and remains a work in progress, these physicists are making strides. As we delve deeper into this mystery, stay tuned here, and we'll keep you informed.